Recall that we have the following relation between the response variable y and the predictor vector x. Y is equal to f of x plus epsilon. Y is the thing we want to predict. X are the predictor variables that will help me to make better predictions. If I want to predict y using x, I need to know this function f, the regression function. The big problem is that f is unknown. I don't know f, and actually I can never know exactly what is f. The best I can do is I can find what I call f hat, the estimation of the unknown regression function f. How do I get f hat? I use data, I use statistical methods. Maybe very simple statistical methods, maybe extremely complicated methods like deep neural networks. I do something to get f hat. And then I hope that f hat is more or less the same as f, that the difference between f hat and f is not too large, because it means that if I use my estimate f hat, I get more or less the same values than which I would obtain if I was using the correct function f. So that's in a nutshell what is happening in statistical learning. You do stuff and then you obtain f hat. How do you use f hat? Well, you are doing the following. Assume that you have to predict the response y, and y is unknown, the number of claims next year, the value of Bitcoin next year, and so on. What you do is you say, well, I am going to predict y using y hat. What is y hat? Y hat is your function f hat, which is now known to you, because that's a function that you obtained using your statistical method. You apply that function f hat on the predictor vector x. And if x is known, it means that if you have information on your predictor variables, for example, for your policyholder, you see that it is a male, it is 20 years old, it lives in Chicago, and so on. You all have this information on your x. You know your f hat, that is the function you just calibrated using your favorite statistical method. Then you can calculate y hat, meaning y hat is then a number. It means that given the predictor variables, meaning given the observation, the new observation you have, you can predict y hat using f hat. If we want to predict our response variable, I can use now my f hat. That is what I have at my disposal, the best I could get from the data. Then the question is, when are we happy with f hat? Meaning, when is f hat accurate? Well, we are happy with using f hat if my prediction, f hat of x, is close to what it should be, meaning it is close to my response y. Think of y as the number of claims in the future. Then f hat of x is my prediction of the number of claims in the future based on the predictor variables I have available of my policyholder. When if my prediction is close to what the future number of claims will be, well, then we did a good job. However, look at this statement, f hat of x should be close to y, close. The question is then, how do we quantify close? What is close? It means that in order to assess the quality of our predictions, we need a measure for closeness. We need to measure distances. Here is my prediction, here is my observation. They are close or they are not close. We have to quantify that in a mathematical way. If we predict the response variable y using a prediction f hat, we need to measure the error. How accurate is our prediction? And on this slide, I will discuss 3 different ways of measuring the error. The first one is the squared error, and that is the most well-known error function. You start from y, the response, the thing you want to predict. You take the difference of y with f hat, your prediction, and then you square that difference. It means you make it always positive, where smaller values mean that your prediction is very accurate. The larger the values of that square difference, the worse your prediction is. So that's a very good error that you can use. However, you can also say, well, let's use the absolute error. And the intuition of the absolute error is the same as a squared error. It's something positive, where small means you're doing a good job. If you see the absolute error increasing, it means that your prediction is not that good. The difference between the squared and the absolute error is that instead of using the square, you're using absolute values. What both functions or both errors have in common is that they are symmetric. It means that if you have to predict y, your prediction f hat is probably not exactly the correct value. Maybe it's a little bit above, maybe it is a little bit below your value you are trying to estimate. However, the effect, the penalty that you get when you are a little bit above or a little bit below is the same, right? So the squared and the absolute error function are looking at the deviations, but not at the direction of the deviations. It could be that you say, well, actually, if I overestimate y, that should be penalized differently than when I underestimate y. For example, if y is your risk level, you want to estimate, well, how risky is my investment portfolio, then it's better to overestimate the risk, to be on the safe side, than to underestimate the risk. If you think you are in a very risky situation, while it's actually a bit better, probably you will make some modifications to your portfolio to protect your portfolio. That is better than when you think you are safe, while you are in reality you are not. Right? So in order to deal with that type of problems, you cannot use a squared or an absolute error. You need to introduce a new error that is not symmetric anymore, that penalizes underestimation differently from overestimation. If we use classification problems, we can also not use squared or absolute errors. If you do classification, y is a class, red, yellow, or blue. Then if the prediction f hat is different from the class, I cannot subtract these two. Y minus f hat in the case of classes is not defined. In that case, we can say, well, let's use the 0,1 loss function. That tells you, well, if you correctly classify, so if the class y you are trying to predict is exactly equal to f hat, the class that you predicted, well, there is no loss. We put 0. If you misclassify, so if y is different from f hat, well, your penalty is 1. Then it doesn't matter what other class you took, you misclassified, so we put error 1. Assume we define the loss function L in this way. We use the squared error, and then the function L gives for each y and for each f hat the squared error between the response and the prediction. Note that x is a vector with your predictor variables, but x is a random vector. What does that mean? Take the example of the car insurance portfolio. You have a portfolio and you have policyholders in that portfolio. For each policyholder, I have a different vector of predictor variables. You have males that are young, you have males that are very old, females with different ages, and so on. If I now look at x, it means that at a random vector x, it means that I'm going to randomly pick someone for my portfolio. And because I randomly pick someone, I don't know what predictor vector I will get. I don't know if it will be a male or a female, for example. That depends on the distribution. So this x is a random variable, so it means that also f hat applied on x is a random variable. It means that what my prediction will be for the future number of claims is not decided, is not a real number. It depends on what policyholder I will get for my portfolio. So I randomly pick a policyholder for my portfolio. That's why X is a random vector. And then I make my prediction. Y is also a random variable. Recall that Y is equal to f of X plus epsilon. It means that there are two sources of randomness in Y. First of all, it's coming from X. Because I don't know who will be my policyholder that I draw randomly for my portfolio, I don't know what Y will be. For example, the number of claims that you have the next year can depend on the sex of the policyholder. Males have more claims than females. If I am going to randomly pick someone for my portfolio, I don't know if it will be a male or a female, so I don't know if Y will be on the higher or the lower side. Alright, so that's the first part of the randomness. However, once I pick my policyholder for my portfolio, my X is not random anymore. I can observe the characteristics of X. I know it's a male, I know he is 50 years old, and so on. However, even if I know my X, I still have uncertainty about the epsilon. Even if I know X, Y will still be a random variable because of the error term epsilon. Alright, so then what is the criterion to say whether I have a good or a bad prediction? It means that if I look at this error here, the loss function, it's also a random variable. How well I will predict depends on what is my policyholder. Maybe I'm better in predicting number of claims for males than for females. Right? So depending on whether I have a male or a female, I have a good or a bad prediction. And it depends on the error term. If that error term turns out to be very large, well, probably I make a bad prediction. So what I will look at is the expected error. What will be my error on average? And then the problem is that I'm looking at this minimization problem where I look at the minimum of my expected prediction error. I'm looking for the function f hat such that my expected prediction error is minimized. It means that I'm looking at a function f hat such that if I randomly pick someone for my portfolio, I get a prediction error that is on average as small as possible. On the previous slide, we talked about this expected prediction error, which tells us how well are we predicting a randomly sampled policyholder from our portfolio on average. However, the expectation here is over X and over Y. So in order to make life a bit easier, we can use the law of total expectation, and instead of taking one big expectation over all the randomness, let's take two expectations. First, let's focus on this inner expectation. In this inner expectation, you have this conditioning on X. What does that mean? Conditioning on X means from now on, we are going to do as if we know X. It means that instead of saying, well, I'm going to randomly take someone from my portfolio and then I will make my prediction, I'm now saying, well, I already took someone from my portfolio. If you already took someone from your portfolio, it means that you can observe the characteristics of this given policyholder. It means that you know that this policyholder is a male, is 50 years old, lives in Chicago, and so on. So the vector X, which was initially random, is now known to us. It means that this inner expectation here, the only randomness, is Y. Y is the random vector. But if we use the randomness of Y, we can use that we know already X. It means that this expectation here is an expectation over the random variable Y given what we know from X, is a conditional expectation. And then once we calculate that expectation, we know everything we integrate over the Y, because in expectation over Y, what remains is an expectation over x. Right? So we look for an expectation for a given policyholder. That is the condition on x. And then with the outer expectation, we run over all our policyholders. Okay? So if you want to minimize this thing here, we can also look at this thing here. Well, what we will do now is we will say, instead of solving the previous problem, where we are looking for an optimal function f hat, now we will move to a pointwise optimization. So instead of finding or optimizing a whole function, we are now only optimizing over a single value of that function. It means that we say, well, let's assume that we know x. So what we will do now is we will do a pointwise optimization. So instead of saying we optimize over the function f hat, so we are looking for the best function f hat such that the prediction error is minimized, we will now say, well, let's assume x is equal to some vector x, and we only look at this optimization problem. So we are optimizing not over f hat the function, but over the value f hat of x. It's a pointwise optimization. We are only optimizing one point on our function f hat. And it turns out that we can solve this problem rather easily. In order to solve that pointwise optimization problem, we can define the function g as follows. So g is your expected prediction error for the predictor variable x. So if we want to optimize over g, it means that we have to check the first order condition, meaning that the derivative has to be 0, and we can also check the second order condition to make sure that we have a minimum. So let me solve the first order condition. So first of all, we can look at the derivative dg df hat x. So we are looking at the derivative of g in f hat. Well, we can write this as an expectation. We change the expectation and the derivative. We take the derivative of a squared function. It's 2 times y minus f hat of x. We have a minus sign, so we have to put a minus sign here too. And we have the condition x equal to x. Okay, this we can write a bit further. We can write this as minus 2 the expectation y given x is x, because we can use the linearity of the expectation, plus 2 times f hat of x, because x is known to us, so f hat of x is a real number. And then you see that from the first order condition, you find that dg of df hat in x is equal to 0 if and only if f hat, my prediction, is equal to the expectation of y given x is equal to the value x. So this pointwise optimization problem can be solved very easily, and what we find is that my best prediction, my optimal prediction, the prediction that minimizes the prediction error measured through the squared loss function, is the conditional expectation of y given x. On the previous slide, we showed that f hat is equal to this conditional expectation. So what is the interpretation? It means that if you know that the predictor vector is equal to the values in x, so you know this is the observation for which I need to predict the response, then you also know that predicting a response, that's basically it's guessing. You can never be 100% sure this will be the value. It is guessing, but your best guess, your best estimate of that response is exactly this f hat that we just calculated. So for any predictor vector x, I can now say, well, if x is this, then this will be my best guess, my best estimate. Also recall that I said that any statistical learning algorithm has in common that it searches for the regression function f. The regression function, that is the holy grail in statistical learning. And you can never exactly know the regression function. F is unknown to us. Each learning algorithm tries to find the best possible approximation. It means it tries to find f hat. But what we just proved with some simple math is that, well, you don't need to make life very complicated. If you use a squared error function, then this is your f hat. It means any, with a squared error function of course, but any statistical learning algorithm should use this f hat. So it seems our problem is solved. I said any statistical learning algorithm is looking for f hat, but here I prove mathematically what f hat should be. The problem is, however, that in order to calculate this conditional expectation, we need the distribution of y given x. I need the distribution of y conditional on the predictor variables x, and I don't know that distribution. So although I have the mathematical expression for the f hat, I still cannot calculate it in a real life example, and that's where you need your statistical learning algorithms. Statistical learning algorithms will help you to first approximate that conditional distribution and then find the expectation of y given x.